Okay. And if you're ready to go, Jared, I'll just do a very brief introduction the way we normally do, and I'll turn it over to you. Okay. Yeah. Welcome to the Monday seminar, folks. Nice to see you all. Yeah, I'm excited to tell you that today, Jared Bryan's going to give us a seminar. He's coming to us from Cambridge, Mass, from MIT. And the rest of the details of the introduction are in an email, and I'll put in the chat if you happen not to be on the email announcement list. If you'd like to join, you're welcome to. The seminar is open to everyone. We really encourage people to participate, especially in the discussion and question and answers that happens at the end. Especially for early career people, you'll hear me ask you more than once to join the discussion. It's not just for experts. The discussion's often led by experts, like William Frank, let's say. But the discussion's for everyone. So without anything further, let me just say that we would like you to mute, but encourage you to unmute and go ahead and ask points of clarification along the way if you have something. And then we'll save real questions until the end, real discussion points. So thank you very much, Jared, for putting this together, and I'll turn things over to you.
Okay, thanks, Chris. And thank you for the invitation to give this talk. I've been coming to these seminars, for a lot of my PhD, so it's really a pleasure to be on this side of the screen. So what I want to talk about today is my work using seismic velocity monitoring techniques to monitor crustal stress and damage in the Ridgecrest fault zone. This is work that I've done with my advisor at MIT, William Frank, and our collaborator, Pascal Audet, at the University of Ottawa. So just by way of a quick introduction or outline of the talk, I'll start by giving an introduction to the seismic cycle, and in particular, looking at how faults interact with the surrounding medium and how that affects, processes that happen on the fault. And then in particular, I'll look at ways that we can use seismic monitoring techniques to track the evolution of important quantities like stress in the fault zone, as well as damage. And then I'll introduce our particular method for seismic monitoring using receiver functions. So this is a technique that uses teleseismic earthquakes to probe the local velocity structure. And so we'll use that technique mostly for its looking at deeper velocity changes. And then we'll get into the Ridgecrest application, where I'll show some results of crustal stress and damage evolution over about an 8-year time scale in the Ridgecrest fault zone. And then if we have time, then I'll broaden out a little bit and we can look at other places where these kinds of techniques might find good use, like subduction zones or volcano monitoring. So the seismic cycle, we can begin with a sort of simple cartoon where we have this kind of block model, and far field tectonic motion causes stress to accumulate on this planar fault in an elastic medium. And at some point, enough stress is accumulated on that fault that you generate an earthquake. But then that the fault will relock and the stress will build again, and this sort of cycle repeats. And it might be nice if we had a sort of repeatable, simple seismic cycle like that. But of course, this makes many, many approximations. And in particular, it supposes that this fault exists in a completely elastic block. So rheologically, it's very simple. And so the kind of question that I want to center this talk on is, what is happening in the surrounding crust, and how does this rheological complexity or heterogeneity in the surrounding crust affect the seismic cycle? And so there's a couple ways that things that are happening in the surrounding crust we can bring some realism to that kind of model. Perhaps, most obviously, there's not just one fault embedded in the crust here. There's many different faults, and each of these surrounding faults will have its own seismic cycle. So you can see a sort of surface trace of the Ridgecrest rupture here, and there's not just one planar fault. The fault has some structure to it, and there are other kinds of faults that are off here. And each of these, is going to be at a different point in its cycle. The main shock rupture applies some stress change, so some kind of a step change in the stress field here. And that acts as a kind of clock advance and triggers lots of aftershocks in the surrounding medium. And so these aftershocks, of course, also have to obey sort of the rheology of the crust. So, they will occur where conditions are such that seismogenic rupture is possible. So as you increase in depth going here, we're looking at Ridgecrest aftershocks. In the shallowest portion, there's lots of aftershocks, and you go deeper and deeper, and eventually temperatures and pressures are such that the number of aftershocks that you get starts to decrease. And so there's also that portion of the structure of the crust that we have to deal with. And then perhaps most relevant for my work is that the fault is not embedded in a perfectly elastic medium. So faults are surrounded by a damage zone. These damage zones are generated by repeated earthquake rupture, both by localization of strain during earthquake rupture itself, as well as by energy that's radiated away, and strong shaking that induces can generate fractures in the surrounding medium. And what that means is that these fault zones become much more complex. You might have a fault core like this with a very distributed damage zone with fracture density that's not constant in space. So you might have more than one of these fault cores surrounded by this sort of distributed damage zone. And these can be pretty extensive features, up to several hundred meters wide for really mature fault zones. And these are important structures to consider, not just because they'll affect how strain localizes and stress is distributed in the fault zone, but they can also act as they can interact with seismic ruptures in an interesting way, and they can act as conduits for fluids, which can change the stress state in the fault and encourage chemical reactions in the fault, which has an effect on the rheology of fault zone materials. And so in this way, faults are impacting the surrounding crust, but this interaction also goes the other way, where the surrounding crust also has some effect on what happens on the fault itself. So you could have material contrast across the fault or those damage zones, and these can introduce complexity to individual ruptures. Like you could have reflection of radiated waves off of these damage zones, these low velocity zones, and that can interact with ongoing dynamic rupture. Generation of these fractures is also important for understanding the energetics of these dynamic ruptures. And sort of more broadly, beyond just a single rupture, these damage zones can also add complexity to the seismic cycle, where if we consider a sort of homogeneous medium here, we can observe these very characteristic periodic seismic cycles, where you have this kind of constant or characteristic slip rate. And then you add these damage zones, and it can change the timing between events and change the rupture velocity. And so, best to consider the seismic cycle as resulting from this interaction between processes that happen on the fault and processes that happen in the bulk. So if those interactions between things that happen in the bulk and things that happen on the fault are important, then we need some method to understand the evolution of the crust, and in particular, some way to monitor stress evolution and damage that accumulates in the fault zone. And so there's many ways to do that. I mean, there's different techniques for doing that, but the technique that we use is based on measuring seismic wave velocities. So these seismic velocities depend on the material properties. So it's very common to, for example, like do a seismic imaging study, and then you see this reduction of seismic velocities around, around fault traces associated with these damage zones. So you can use the seismic velocities to image the fault zone. Beyond these sort of changes in elastic material properties, the introduction of damage zones introduces sort of higher order effects, so nonlinear elastic effects to the material properties. So this is an example of some seismic velocity changes as a function of forcing frequency, or as a function of, so you can see, there's a lot of seismic velocity change, which is correlated with these different tidal forcing frequencies, is I guess what I'm trying to say. So you can use these kinds of different forcings in order to understand something about the rheology of the material, characterize the stress sensitivity, and yeah, so sort of map those kinds of properties around the fault zone. The way that that's done in practice is by seismic interferometry. And so the idea here is we want to measure the change in seismic velocity through time as a way of characterizing the material properties, the rheology of these fault zone materials. And so we need to get some seismic signal that is more or less repeatable and differs only in the medium that it propagates through. So as the medium changes, we can use changes in these seismic signals to characterize changes in the medium. And so here's an example of a repeating earthquake. You can see there's actually two earthquakes plotted here, two seismic waveforms from a repeating earthquake. And you can see they're very, very similar. And if you zoom in, like to especially later in the coda, there are small little changes, but by and large, this is a repeating signal. But what we want to do is we want to find these very repeating signals and then characterize the really small variations between them. And so you could do that, for example, by scanning through this signal and saying at every time, sort of local lag times as a function of time in this seismogram, you see that you have this linear increase in the lag time of those different arrivals. And so that's indicative of some change in the velocity where, the propagation time of each of these phases is delayed by some proportion, in proportion to the seismic velocity change. So the sort of generic procedure that we're trying to use here is we need to find some reference signal that in some way characterizes the velocity structure of a fault zone. And then we need to find signals that are pretty close to that reference signal that more or less repeat. And then we need to characterize those small deviations as a way of characterizing the velocity change. So you could use repeating earthquakes for that. You could use, you could estimate the Green's function from ambient noise cross correlations. There's lots of different techniques to use, but that's the sort of general approach. And then we want to use those measurements of seismic velocities and track them through the earthquake cycle to learn something about how those fault zone materials behave. So some of the classic observations of seismic velocity changes through the earthquake cycle, first of all, are the signature of coseismic damage. So at the time of the earthquake here, this is an example from the 2019 Ridgecrest earthquake. They're measuring seismic velocity changes through time. And then at the time of this magnitude 7.1 earthquake, there's this big reduction in seismic velocity because the waves that are radiated by this earthquake damage the material. It reduces, it becomes less rigid, generates damage. And so you get this almost 7% velocity reduction. And this kind of affected area of the velocity change can be quite large because the waves can propagate very far while retaining a high amplitude. And so, you might see a measurable velocity change several hundred kilometers away, many fault lengths away. So this can be a pretty widespread feature. Immediately after the coseismic rupture, you also see this post-seismic recovery. So, after you reach this minus 7% velocity perturbation, immediately it starts to recover back towards some pre-earthquake value. Whether it reaches it or it falls short or whatever is of course going to be location dependent. But this is driven by both mechanical processes like recompaction as well as chemical processes like mineralization of these newly opened fractures. And you can see that as you step through in time, this zone of seismic velocity perturbation shrinks and shrinks until, 14 days later, almost the entire Ridgecrest area has completely healed this velocity change. So it's super quick velocity recovery in this case.
Bryan, can I ask a question?
Yeah, please.
So I am a bit confused here because which is the origin of the change in wave velocity? The perturbation in the stress state, or it is the dynamic passage of the seismic waves? Because if it is the former, I would not expect this large effect over a so broad area, because the stress change will be limited to the source volume. But
Yeah,
if you are at 100 kilometers far away, perturbation of the wave velocity, this means that the origin is not a change in the stress state.
I agree.
Just
So this is not an
dynamic
example
change.
of something that's induced by the static stress change, for example. Like this is not an effect of the static stress change. This is due to the dynamic strains from the radiated waves. So that's the source of that shallow damage there. But that's not to say that seismic velocities can't also be stress dependent. So you can look at smaller stressings like from tidal forcing or other things like that that would also induce some seismic velocity change. So seismic velocity changes, will capture changes in the medium. And then it's up to us to say, what is the source of that change in the medium? In the case where we observe seismic velocity changes really far away, I agree, static stress changes don't make sense. So we appeal to other mechanisms. But in other cases, we see that it has, the same period as the tidal forcing, in which case we say, oh, maybe it's this smaller effect due to a stress sensitivity.
Okay, thank you. Very interesting. Thanks. Sorry.
Yeah, of course. So so I was pointing out this really rapid healing of the Ridgecrest fault zone. That healing is important both for things that are happening on the fault, re-strengthening faults due to, for example, growth of contact area, but also more broadly in the medium where these large-scale recovery of the seismic velocities can be observed seismologically. So another thing that is really commonly observed and which, is taken as evidence for seismic velocity changes due to this strong shaking from the passage of seismic waves is that these changes are typically limited to quite shallow depths. So this is an example from the 2004 Parkfield earthquake. These are sensitive to different depths, where the high frequencies are sampling shallower depths, and as you move up, they sample deeper and deeper. And you can see that the largest seismic velocity change at the time of the Parkfield earthquake occurs at these high frequencies and then decreases with depth. But there's one big caveat to this kind of common observation, which is that our techniques for measuring seismic velocity changes don't sample the entire crust. They primarily sample the shallow subsurface. So repeating earthquakes, for example, they might have a very repeated, very well-characterized rupture region, and they produce these repeating waveforms. But these earthquakes don't repeat very often, and they don't occur everywhere in the crust. So they'll be concentrated more toward the shallow crust, just by nature of needing to generate some seismic rupture. Ambient noise is another technique you might use. It's ubiquitous in both space and time, but it also tends to lose sensitivity with depth. So this is an example from some modeling work that I was a part of, where essentially we simulated the wave field from ambient noise, and we constructed these cross correlations to estimate the velocity changes. And then because we did this in a synthetic way with a velocity model, we could apply a velocity change at different depths and see how we could recover that true velocity change as we move that perturbation deeper and deeper. And so the velocity change that we applied was always this kind of fixed 0.1% velocity change. But then, whether we applied that velocity change at the surface or as we slid it down to 1 kilometer, 2 kilometer, 3 kilometers depth, the estimated velocity change was under predicting the true velocity change more and more. And so we also have this effect where deeper velocity change, you just lose sensitivity to them systematically. And so the question that will motivate the work that I present today is, are we missing anything from our understanding of the seismic cycle due to this effect of losing sensitivity with depth of the velocity change? So In order to address that question, I'll introduce a method that can continuously resolve these velocity changes at depth, which is based on receiver functions. So receiver functions are one way that we might think of solving this, where instead of trying to find local seismic sources, we'll take seismic sources that are distributed around the world. So large earthquakes greater than magnitude 5, far enough away, so 30 degrees epicentral distance up to 90 degrees, so quite far away. And these earthquakes radiate waves that go down through the mantle and then arrive at the base of the crust, almost vertically. There's quite a few of these events every year. There's around 1,500 large events every year, and around 1,000 of them, like if we take a station in California, there's around 1,000 of them in the proper distance range and of the proper magnitude. So at least, in theory, there's the potential for decent time resolution. But if we zoom into the last leg of that travel path, the way the receiver function is constructed is that we have this plane P wave arriving at the base of the crust. And some of that, most of that energy from that P wave that arrives is transmitted through to the surface. And what the receiver function does is it measures the difference in arrival time and amplitude between this direct P wave and converted S waves that are generated by scattering at this boundary. So it's a relative measurement between this direct P wave and those converted S waves. So there's some P to S conversion that's generated. It arrives sometime later because the S wave takes longer to travel through this layer. And then there's also this whole slew of reverberated phases that will arrive somewhat later as well. And the really important thing for our purposes is that the receiver function is making use of globally distributed seismic sources. So the source is not constant and the travel path is not constant, which seems to pose a problem for seismic monitoring because we're trying to isolate just the effect of the local seismic structure, but there's all this other information in the teleseismic waveforms. But because this is a relative measurement, before scattering at this boundary, all of the phases that we observe are the same P wave. And so you can remove a lot of that redundant information. And so you're left with something that removes, variability in the earthquake source and the far field travel path information, and you're left with something that just reflects the local seismic structure. We can also look at how this signal responds to velocity changes local to the seismic station. So, for example, this is applying a 2% P wave velocity change, which I showed just to contrast it with the sort of linear increase in the travel time shift that I showed with the repeating earthquake, where even with a uniform velocity change in the upper layer here, these different features respond in a more complicated way, where some peaks are moving to the right and some move to the left and some don't change at all. So, the price you pay for having some seismic signal that propagates from the bottom up here, to give you your depth sensitivity, you pay for in complexity of the waveform variations that it produces. The other main challenge that you take on by trying to do seismic monitoring with receiver functions is that, even removing most of this earthquake source variation and far field travel path information, you're still left with something that's not perfectly repeatable. Even just like, depending on the distance of the earthquake to the station, the incidence angle is going to be different at the base of the crust. And that changes the scattered wave amplitudes, or the back azimuth sense, dependence of the receiver functions will result in, you're sampling an anisotropic crust, or you're sampling dipping layers in a different way. And so there's no way to get rid of that. I mean, I guess what I'm saying is there's no natural reference to measure the deviations of each individual receiver function with respect to. So you take on those challenges by using receiver functions. So the thing we gain by using receiver functions for monitoring is they uniformly sample different depths. So you don't lose sensitivity to velocity changes in depth. But the price you pay are these nonlinear waveform variations, and then this problem of having a mixture of different sources of waveform variation that you have to disentangle later. So in order to address those two challenges, I'll introduce a method based on the theory of optimal transport. And then we'll get to the Ridgecrest example, I promise. Okay, so fundamentally what we're trying to do is we're trying to measure the difference between two signals. We have some reference signal and we have some signal that has been perturbed in some way. So how do we do that in a way that lets us accomplish our goal of measuring the seismic velocity changes? Well, the sort of most naive thing we could do, like the most direct approach we could take, is to just measure the difference between the two signals in a sort of standard Euclidean sense, where we basically just compare the amplitude between the signals at each individual lag time, which does not really capture the character of the time shift between these two signals. So it's not useful for capturing things like time shifts. The signal that, or the method that we've been working with based on optimal transport essentially tries to come up with some more general transformation between the two signals, where you take this black signal and you try to transform it into this blue signal in a way that minimizes the amount of work that you need to do to do that transformation for some notion of work. And so this kind of more general transformation allows you to take into account both time shifts as well as amplitude changes, and sort of more completely capture the character of these waveform variations. So that's one thing. But the other nice thing that you get with using this optimal transport method for comparing the differences between these signals, and it's a kind of a technical point, but we make use of it, so it's an important point, is that measuring the distance between two signals, you're choosing a metric. And by choosing a metric, you're giving this space of waveform variations a geometry. And you want to choose a geometry that simplifies your problem. So by choosing this optimal transport metric, we're essentially saying each of these receiver functions that live in this complex space, and they vary along multiple dimensions in a nonlinear way. There's some mixture of back azimuth variation and velocity changes. Choosing this particular metric allows us to define some transformation of this signal, that we can embed this nonlinear space into a linear space in a way that preserves information. So we don't throw away any information by doing this. And we like living in a linear space because it lets us use standard linear unmixing techniques like independent component analysis, where we can separate these different modes of variation. So the way that we do that is we might have some set of receiver functions that varies here, both the incidence angle and the velocity change varies. This is a synthetic receiver function example. And we make this projection into this linear space, and we take two independent components, and we see in this space here, we can completely capture this signature of the velocity change onto one of these independent components, and the signature of this incidence angle change onto this other independent component. And then once we've done this separation, we can just nullify the information contained in this component that captures the incidence angle variation. And we can reconstruct these waveforms as if they all came from the same place. So that's the goal of doing this whole procedure, is that we want to remove all of this nuisance variation and just isolate the part of the signal variation that comes from velocity changes. Okay, so thanks for bearing with me through that section. We can get to the Ridgecrest example then.
Jared?
Yeah.
Chris, just a quick point, and we can come back to this later, but you say, you want to just get at velocity variations, but you also are taking advantage of amplitude variations, right? Or are you saying those amplitude variations are all part of the source?
So we're also capturing the amplitude variations, but velocity changes will also affect the amplitudes, because if you cause some velocity change, that can change the scattering properties at layer boundaries, for example, and that can change the strength of the scattered phases. So I'm not in doing this separation, I'm not making a separation between time change and amplitude change. I'm making a separation between independent time amplitude modes of variation. So they'll both mix time and amplitude changes.
Yeah, okay. Okay, thank you.
That's what makes it challenging in a lot of ways. Okay. So the 2019 Ridgecrest earthquake sequence is a sequence of two major earthquakes. There was a magnitude 6.4, followed 36 hours later by this magnitude 7.1. You can see the sort of surface trace of these faults on the left-hand side, and then a representation of the surface displacement observed geodetically on the right-hand side. And here's a finite fault model of the main shock rupture, or at least one of the faults from the main shock rupture, where you can see there's a lot of slip, but mostly concentrated above around 10 kilometers. There have been studies in the past on seismic velocity changes for the Ridgecrest earthquake. I showed some of them earlier. This is a study which used aftershocks from the Ridgecrest earthquake, and in a very similar way to the receiver function work that I'll show in just a moment, they're looking at these converted phases generated at this interface at 2 kilometers depth, so that they're measuring also some relative arrival time between a direct phase and these converted phases. And they use this to track the velocity changes in super high time resolution over around 14 days. And you can see some variation along strike of the main shock rupture here, but generally there's a really big velocity change and then really rapid recovery. So within about 14 days, most of the fault zone is completely recovered. And then if we look at some other studies which expand that time to about a year of seismic velocity changes. So the previous one was 14 days of seismic velocity changes. You can see this is a study using ambient noise autocorrelation, so also measuring shallow velocity changes. They also see this big coseismic velocity reduction at the time of the earthquake at the red bar here. And then within about 2 or 3 months across the network, they see complete recovery of this seismic velocity change. So, but like I said, both of those observations are measuring primarily the shallow velocity change. And the question I want to address is what's happening below this, strong shallow seismic velocity change. So I calculated receiver functions for 34 stations across the Ridgecrest fault zone. So here I'm showing a station at the northern edge of the rupture there, WRC2. These are the receiver functions. The color map here is the amplitude of the receiver function. And you can see I've stacked those receiver functions before and after the earthquake down here. And you can see there are these really consistent phases that come in. These are associated with these interfaces, some velocity contrasts in the crust and different reverberations. And you can see these are pretty stable through time. And then at the black line here is the 2019 Ridgecrest earthquake. You can see these strong changes in some of these phases, especially as you move later in lag time. These strong changes in the arrival time of these different phases and the amplitude of these phases can change very strongly. And so this is a signature of some velocity change that's, being experienced by the medium here. So the question though is, what velocity change is causing these waveform variations and where does it occur? How does it evolve through time? So what we need to do is we need to follow that kind of procedure where we take our receiver functions and we embed them in this space and we come up with these different independent components of the waveform variation. And then what I do is I go through and I select different components that show some time variation. So for example, independent component 1 here, it has some sinusoidal variation in back azimuth, maybe some mild slowness dependence. But there's this strong variation here for this component in time. It shows this strong step change at the time of the earthquake. By contrast, the second independent component doesn't show anything really strong happening at the time of the earthquake. And so I just take those that don't show time dependence, and I sort of remove that component of the variance from the waveforms. And so what that does is it allows us to reconstruct these receiver functions just along the time-dependent axes. And you can see that it emphasizes these really clear phase delays, especially in the later part of these receiver functions. So I've colored these by before the earthquake in blue and then after the earthquake in red, and you can see this really clear time delay there. Okay, so the question though is, at what depth does this velocity change occur? What's the magnitude of that velocity change? And so in order to get at that, what we did is we inverted these receiver functions for some layered velocity model. And with that layered velocity model, we can construct some synthetic waveform, and we can apply changes to this velocity model and see how it affects the synthetic waveform that we generate. And so that's what I'm showing here in this bottom plot, where essentially I'm saying I can apply some velocity change at a given layer. Let's say I apply a velocity change at 5 kilometers depth. Then, where does that difference show up in the waveform is shown by the color map. So if I apply a velocity change at 5 kilometers depth, it changes the waveform at 2 seconds, and then a little bit later at around 6 seconds. And so if we want to explain these large changes that occur at these later lag times, either they follow this first move out associated with these direct converted phases, in which case the velocity change would occur down here at like 50 to 70 kilometers depth, which is probably too deep, or it follows this other move out associated with the reverberations that occur in various layers in the crust. And in that case, we say, okay, we want to explain these changes that occur, primarily after 7 seconds. Well, the depth associated with those is something like 10 to 20 kilometers. And that's sort of a schematic, description of the kind of approach that we're taking to locating the velocity changes that we see in the receiver functions. And I'll do that in a more with a real inversion in a couple slides. Okay, so how does that velocity change evolve in time then? So here I'm essentially recapitulating the result from the ambient noise autocorrelation velocity changes here. So here I'm showing this optimal transport distance as a function of time for the ambient noise autocorrelation. So this is something that's sampling just the very shallowest subsurface. This is not from a receiver function. This is something quite shallow. So you see there's some variability, but there's this really strong coseismic perturbation to the ambient noise autocorrelation, and then it heals really quickly. And within about 2 months, the perturbation to those waveforms is back at more or less pre-earthquake levels. So here I'm showing then the change in the waveform from the receiver function results. So I'm showing this for 2 different segments of the receiver function. So so the blue curve here corresponds to the early part of the receiver function in the first 5 seconds. And then the red curve corresponds to the later part of the receiver function there. So it's sampling different travel paths. So for the early part of the receiver function that samples these direct converted phases and these and similar for the deeper reverberations later in the receiver function. But initially, those deeper reverberations don't have as much of a perturbation as the shallow changes, or as the earlier changes, I should say. But at some point, those switch. The inequality switches between the two, where the red curve overtakes this blue curve. And then the other thing to point out is that, relative to this pre-earthquake level, even several years after the earthquake, there's this constant offset, and you don't get this full recovery from the receiver function measurements, just by using the same station for these different measurements. We can measure the size of this change across the fault zone. So here I was showing the station WRC2, but we can make this before and after comparison for all these 34 stations, and you can see some general, in general, like the largest perturbations are located closer to the fault, and then there's some sense of decay as you move from the fault. So that's what we would expect. Okay, so then we can take those waveform changes and then invert them for the velocity change that happens at depth. So instead of doing it schematically like before, now we've done some grid search over different combinations of velocity changes in different layers, and I'm showing you the results of that here. So in the shallow subsurface, you get this classic large coseismic velocity change, and then this pretty rapid recovery over the post-seismic phase. Was imaged with the ambient noise autocorrelation about 6 months, but the overall takeaway is the same, which is that, there's not much happening before the earthquake, and then within a few months, it's completely recovered in the shallow subsurface. Okay, so by contrast, if we look at the velocity change that occurs in the deeper part of the crust, so here there's a bin here from 10 to 15 kilometers, we see that there's no big coseismic velocity change, and instead this velocity change accumulates over the post-seismic phase. So after this shallow velocity change has fully recovered, this deeper velocity change remains in this perturbed state, and you don't need any shallow velocity change to explain, perturbations to the early part of the seismic signal, and the only thing that's left is this deeper change that accumulates post-seismically. And so what we want to argue is that this depth-dependent response to the earthquake is capturing some depth-dependent rheology of the fault zone materials, where you might have this sort of classic brittle damage and healing, whereas this is something which accumulates, more gradually over time. And I just want to point out that this transition, between these two types of behavior is quite close to where we get this transition between, the concentration of coseismic slip to less slip below. So then before I spend too much time interpreting that result, I want to introduce one more observation, which is something that we threw away before, which is this back azimuth variability of the receiver functions. But that captures interesting information. In particular, it captures anisotropy in the medium. And insofar as that anisotropy is related to things like oriented veins or fractures, those are defects that are generated in the medium in a stress field. And so they capture the stress field in some way. And so the hope is that, if we can measure some time dependence to the anisotropy, we can use that as some method of measuring the evolution of the stress field in the medium. So you can see here a bunch of receiver functions that I have stacked depending on the direction that the arriving waves are coming from. So as you move from north, south, back around, you can see these really clear time delays in changes in amplitude of these different phases in the receiver function. And so we can fit these back azimuth dependent receiver function amplitudes to estimate, what's the fast axis direction, in what direction do these waves propagate the quickest, and try to measure that through time. Okay. So I estimated the orientation of this anisotropy. This is a fast axis orientation for a bunch of stations across the Ridgecrest fault zone. You can see predominantly these fast axis orientations line up with regional tectonic structures. So they line up pretty well with the main shock rupture plane, for example. And then as you move to the south, they rotate to this more east-west orientation along the Garlock fault, and then rotate back to this more northwest, southeast orientation as you move further south. So it's plausible, I think, that these reflect local, tectonic structures, something that reflects the stress field in some way. We can do the same thing we did with the isotropic velocity change, where, we take the receiver functions before the earthquake and the receiver functions after, and we separately measure this orientation. and then measure the difference between those to see, you know, how much does the earthquake rotate this fast axis orientation. And we see a maximum rotation of around 7 degrees here, up to 10 degrees maybe if you go to the edge of that error bar, which then, you know, the largest rotations are located near the fault, and then there's some sense of decay with distance like that. And so I think that is consistent, at least, with this being due to some stress change source. We can also try and slice this even finer, where, you know, we take some moving window and we estimate the fast axis orientation through time. So you can see that here for these receiver functions before the Ridgecrest earthquake, and then in red for after the Ridgecrest earthquake. And what I want to point out, or what we argue, is that there's not really a clear, consistent coseismic change in this fast axis orientation. So obviously there's a lot of scatter. You know, it's a very difficult measure to make, but, you know, there's not some super clear coseismic reorientation. And if anything, there's some, you know, gradual rotation, some accumulated rotation that occurs over a similar timescale, say 6 months or a year, as this orientation rotates. And we plotted that against this GNSS displacement rate. So that's just all to say that, you know, when you have the largest slip rates is when you're rotating these fast axis orientations. Okay, so then, yeah, by means of interpretation then, so what does that mean for the rheology of the crust? I think we saw this depth-dependent, you know, this contrast in how the seismic velocities evolve through time, which is different for the shallowest subsurface versus this sort of mid to lower crustal velocity change. That contrast in the time evolution of these velocity changes seems to correspond with a compilation of where coseismic slip is dominant in the shallow crust versus after slip, which starts to become the dominant form of deformation as you move deeper. That also takes place at around 10 kilometers. And so it suggests that maybe the rheology of this fault zone material plays some role in bounding the coseismic rupture, at least in depth. Then finally, what we can try and do is, you know, we're making some estimate of the timescale of this mid-crustal deformation. And so we can try and see, you know, what does that mean for the sort of large-scale strength of the crust? There have been other estimates of the crustal strength based on things like focal mechanism rotations or more general kind of stress inversions. And typically what they see is that the upper crust needs to be quite weak. So maybe a maximum of, you know, 4 megapascals of supported shear stress before the earthquake. Then the stress drop is not very big, but it still rotates the orientation of these focal mechanisms. So, you know, that's an argument for why the upper crust must be pretty weak. Then what we tried to do is we tried to take that time scale of the observation of the mid-crustal, you know, velocity change that we observed, and then say, okay, if that deformation is occurring, you know, let's take a meter of slip, you know, based on GNSS displacements, and we assume some width of that deformation, then that gives you some strain rate that this material is experiencing. And then we ask, you know, for different mechanisms of deformation, so for different rheologies that you might assume, what's the driving stress that you would need in order to produce deformation at those strain rates? So for some range of different strain rates, we can assume different rheologies of the material. And all that I want to point out here essentially is that, you know, whether it's deformation by dislocation creep or you invoke something like low temperature plasticity or something, where these curves intersect, you know, this bound of possible strain rates tends to be at quite high driving stresses. So something like 100 megapascals to a gigapascal or something like that. And so at least based on, you know, the sort of timescales and the observations that we make, it would suggest that rheological contrast may also correspond to some change in crustal strength. So then just to summarize, we used receiver functions to measure seismic velocity changes. You can see those velocity changes in the change in the waveform. We tried to locate those velocity changes, and we saw this difference in how those velocity changes evolve depending on depth. And in particular, there's this mid-crustal velocity change that shows this kind of opposite time evolution with this that accumulates over the post-seismic phase and then remains perturbed long-term. Yeah, so that long-term perturbation to the seismic velocities, maybe it persists, over interseismic timescales. Maybe it takes a long time, the full interseismic period to recover back to where it was before the earthquake. In any case, it persists over the observational timescale. And then finally, we tried to show that, that rheological contrast may also be a strength boundary where you have this very weak upper crust, and then as you move down in depth, you have some zone of very strong crust before weakening again. And so, let's see, I've been talking for about 50 minutes. I'll just really quickly go into some future applications, I think, of these seismic monitoring techniques, where especially measuring deeper velocity changes might be useful. And so, in particular, I think subduction zones are one place where this would give a lot of information. There's been some work by our collaborator Pascal Audet and his group looking at seismic velocity changes during slow slip events. In some ways, this is like the natural place to measure receiver functions, because you're looking at changes that are occurring, on a boundary on the plate interface, and so they generate a strong converted phase. And what this group did is they looked at seismic velocity changes, after slow slip events. And when you're close to a slow slip event, let's say at 20 days after the slow slip event, there's some measurable perturbation, but then that decays through time. And so you can use that to try and make some estimate of the pore pressure change, or look at some change in the material properties that occurs during these really interesting events. They've done some other work, for example, at the Hikurangi subduction zone, trying to measure, not wrapped around multiple slow slip events, but for individual slow slip events. And they see this really striking correlation between the receiver function power, which is related to the strength of these converted phases, and the GNSS surface displacement. So you can see these really clear, I think, correlations between those two properties, which I think is a very exciting way to try to measure, evolution of pore pressure and other processes that are happening, typically, below where we can measure these seismic velocity changes with other techniques. Volcanoes are also a very interesting place where I think these could find application, especially in looking at not, below just these upper crustal magma reservoirs. Transport might occur. So both for understanding the rheology of these lower crustal melts, as well as for, earlier precursors, I think would be a very interesting future direction. So with that, I'll put up some conclusions, and welcome any questions that you may have. Thank you all for your attention.
Jared, great talk. Thanks so much. I will invite people to unmute if they'd like and join me in thanking Jared for, really, really beautiful talk. Thank you.
William's got a question.
No, I think he's waving. Yeah, well, okay, so easiest approach is to use that raise hand feature you see at the bottom of your screen. I suppose you're all experts at Zoom, but if you're not, that's what it looks like. That'll put us in some order to ask questions and have a discussion. And absolutely want to encourage everyone to join the discussion. If you've got a question of some sort, maybe you've got a clarification, maybe you've got something else. Yeah, please. Manuel, please go ahead.
Hello. Thank you for your very nice talk. Could you go back to the time series of the about the anisotropy, the fast axis that you have measured with the fast axis rotation. Yeah, exactly.
Uh-huh.
This one. So are these data are for a single station, or is this like the average of all the stations in the area around the Ridgecrest earthquake?
For this time series, it's just a single station. So,
Okay.
we for each station, we take some 180-day moving window and we measure the fast axis orientation. But, so we do that for all these different stations. So you can see, back when let's see, showed the anisotropy. Like here, for example, these are all separate stations that we measured the fast axis rotation at, but just as well, we have the time series.
All right. Yeah, thank you. And so these rotation, so these basically these data are taken from the converted phases where at the MOHO or some shallower interface.
Yep. Yeah. So we don't make any. I mean, part of inverting the receiver functions for some velocity structure is that we can associate those phases with individual boundaries in the crust. But typically, yeah, we're just assuming these are all crustal conversions. So you can generate a converted phase at the MOHO